Hey everyone, welcome back to another video. In this and the next video, we will learn what is thread safety. This is a very important topic because in this video, we will learn what all things can go wrong in a concurrent program. So if you understand the patterns, if you can identify the things which can go wrong, it will help you in the long run. And since there are many things to cover, so I have divided this topic into two videos, so make sure you watch both of them. Let's get right into it. So any concurrent program that we write or any multi-threaded system that we design has to be thread safe. But what exactly is thread safety? Here on the screen, you can see a definition of thread safety. It says that thread safety is about a piece of code that does what it was supposed to do even when accessed by multiple threads. But what does it mean? What do we mean by a piece of code, and what is the meaning of it does what it was supposed to do when accessed by multiple threads? So here a piece of code could be a simple class, or maybe a whole module, or maybe a functionality, a system, a business flow. So the expectation is that this piece of code or the functionality will do what it was supposed to do. It will do its job correctly even when accessed by multiple threads. Now the question is, what does it mean and what exactly are we trying to keep safe and from whom? So let's understand this with the help of an example. So here we have a very simple class account which has an instance variable balance. Then it has two methods, credit and debit. We understand in Java a class encapsulates the behavior and the data. And this data is also called the state of the object. Not all the variables represent the state of the object, only the instance variables or the static variables represent the state of the class. So here you can see we have a single instance variable which is the state of this account class. So when we create a new instance of the account, let's say A, it will have a default value of the balance, let's say 0 or something else, XYZ, for example. Now, whatever operations are performed on this instance, let's say O1, O2, O3, maybe O1 called the credit method, okay? Then as an operation O2, someone called the debit method on this object, then again credit. So you can see, and let's say there is this end of the object. So as you can see here, object A is going through all these operations, and what we are essentially doing is we are updating the state of the object. Here all these operations are manipulating the state of the object, and this state is basically the balance field which is going through all these operations O1, O2 and O3 as part of the method calls credit and debit. Then the field of the objects also have invariants which must be obeyed and followed as the object goes through different states. What that means is, for example, in this case, there is a single field which is the balance, which represents the state of the class, and the invariant associated with this field is that the balance should always be greater than 0 for the account. If the balance goes beyond 0, I mean if the balance becomes negative, then it represents an invalid balance. So the condition for the state of this object is that the balance must always be greater than or equal to 0. That is the invariant which is associated with this balance variable. So this is called invariant, which must be followed and obeyed for any object. Now there is something also called precondition and postcondition. What that means is, for example, if we talk about this method debit here, so the precondition is for this method is that the balance must be greater than 0. If the balance is already negative, then we should not perform the debit operation because it will make the balance negative. So the precondition for this method is that the amount or the balance of the account should be greater than 0. And similarly, there will be a post condition, okay? So it will be something like, let's say if we execute this method and the precondition was the amount should be greater than 0, all right? Now, if the amount is greater than 0 and if we call this method, it will complete its execution. Then the post condition, the expectation is that the balance after the deduction, after the debit operation should be greater than or equal to 0. It should not be negative. So as you can see, there is a check here that let's say if balance minus amount is less than 0, if it is going to be less than 0, then in this case, this is throwing an error. This is just a very simple and a sample implementation to showcase the concept of precondition and post condition. All right. So the post condition in this case for this method would be that the balance should be greater than or equal to 0. It should not be negative. And similarly, all the classes that we will write will have a state, and the methods will have the preconditions and post conditions which must always hold. Now, even if a class doesn't have a state, let's say there is a class which does not have any instance or static variable, even in that case, the methods that we define have the preconditions and the post conditions. That's how we make sure that the class or the state of the object always remains consistent. So we covered the concept of invariant or the conditions for each field of the object and the methods which have the precondition and the post condition. Now you don't write the preconditions and the post conditions explicitly somewhere, but this is the you can say something that is understood implicitly. Okay. Now we can go back and try to understand the definition of thread safety, which was something like a piece of code which does what it was supposed to do even when accessed by multiple threads. What that means is, let's say if we talk about this piece of code, so we now understand the concept of invariant, precondition and post condition. So what thread safety says, as per the definition, this piece of code, for example, will be called a thread safe code when, let's say, if it is being accessed by multiple threads in a concurrent setting, even then, if the precondition and the post condition remain consistent, remain true, and they follow the invariant of this class, which means the balance should be greater than 0. So if a piece of code is always following the preconditions and the post conditions, and it also follows the invariant of the state, okay, even when accessed by multiple threads, then that piece of code is called a thread safe code. That is what we mean by keeping the state safe. Okay, but why would this happen and how could this happen? Let's understand that as well. So we understand the concept of object creation in Java, how the objects are created and stored. Any object that we create will be stored on the heap. So here on the heap, we say there is a single object of class account. So this is the account object and it has the state, that means the instance variable balance. Now, as we can see, there are two threads, T1, here it is, and T2. So this is T2 thread. Okay, since the object is stored on the heap and if multiple classes have the reference variable of the same object, then we know the object will be shared across those classes which have the reference variable. So let's say from the main method or from the entry point, whatever it is, we created a new thread. Let's say there are two concurrent requests on the same account. So we created a new thread and this thread is acting on the account object. All right, let's say it is calling the method credit. All right, and at the same time there was another concurrent request which will be handled by second thread for the same account, and let's say the request was for debit. So in this case, we know both the threads T1 and T2 are acting on the same object, so that means this object is shared between both the threads. And since both of them can access the same object, they can also change the state of the object. So that's what we mean by when a piece of code is accessed by multiple threads. So when multiple threads have the reference variable or access to the same object on the heap, they can mutate or change or update the same object. Now think about it, what would happen since T1 and T2 both can access the same object on the heap. Let's say T1 was reading the balance and at the same time T2 was updating the same balance. What would happen? Will the T1 read the updated value or it will read the stale value? So that is a question. Now the second scenario could be what happens when both the threads are updating the same value. So T1 is also updating and T2 is also updating. Let's say T1 had the value V1. Okay, so it was about to update the balance, and similarly T2 had the value V2. Now what would happen? What will be the final value? Will it be V1 or will it be V2? So it depends which thread performed the action first and which thread got the chance to execute later point of time. Now the final value of balance, whether it is V1 or V2, depends on the order of thread execution. And we understand this is highly non-deterministic. It totally depends on the JVM runtime and the operating system scheduler in which order the threads will execute. So at this point, there is no way to tell which thread will execute when and whether the value will be v1 and v2. So whenever the object is shared across multiple threads and any thread can mutate the state of the object, we always need to think about the risk of thread safety, because it could happen that the state will not remain consistent, it will not follow the invariants, the preconditions and post conditions, because the order of the thread execution totally depends on the runtime and we have no control on it. Now that we understand the concept of object state and we saw how the objects can be shared across multiple threads and any thread can attempt to update the state of the object which may impact the operations of the another object. So all in all, we can say that the thread safety is about protecting the state of the object on which the threads are working. Number two, it is about making sure that invariants are obeyed and followed. We already covered the concept of invariant, in which the state has a condition that must always remain true. Okay. And number three, transitioning from one valid state to another. So any method, any public method that we write, okay, it must transition the state from one valid state to another. And the same holds true for any system or any module. Here we are talking about the class, but the same holds true for any module or system. So it's all about the state. When the object is shared across multiple threads and the state of that object is shared and mutable, then thread safety will always be a risk, will always be a concern. Let's go to the whiteboard and spend some time on this concept. So here in this example, we have two objects on the heap. Then there are two threads T1 and T2. Suppose A1 reference variable is pointing to this object and A2 reference variable is pointing to this object. What that means is that in this case, T1 and T2 are working on two different objects. They have nothing in common. So here objects are not shared between T1 and T2. What that means is, let's say if T1 is updating the state of A1, it will not impact T2. And similarly, if T2 is updating the state of object A2, it will not impact T1. So when nothing is shared between threads, it will always be thread safe. Okay. So we need to understand two keywords, shared and mutable. If nothing is shared, then we don't need to worry about it. That we saw in this example. Here T1 and T2 are working on two different objects, so there is nothing to worry about. Now let's talk about the mutability. What that means is, suppose now in this example there is a single object on the heap and threads T1 and T2 are referring to the same object. So in this case the object is shared, but the condition is it is read only. What that means is that the state of the object cannot be mutated, cannot be updated. So if something is shared, but if it is immutable, that means the state of that shared object cannot be mutated and cannot be updated, and it is read only, then that condition is also thread safe. Okay. So in the previous example, we saw the objects were not shared. If something is not shared, then it is thread safe. And if something is shared, okay, but it is immutable, if it is read only, then also it is thread safe. The problem is when something is shared and that is mutable, that means it can be changed. So if something is shared and it can be changed, then there is a risk of thread safety. Okay, so whenever you are dealing with a concurrent program or a concurrent piece of code, always focus on the state and identify if the state is shared and mutable. And let's say we find a condition like that, how do we make sure that it remains thread safe? Let's see that. So when we find a condition where the state is, let's say, shared and mutable, and we have to protect the state, then we have three options. Either we do not share anything, that we already covered. If something is not shared, then it is thread safe. Number two is do not mutate. So even if the object is shared, but if it is immutable, if we cannot mutate or update the state of the object, then also it is thread safe. And the number three is, suppose it has to be shared and it can be mutated, then how do we protect the state? Well, if the object has to be shared and it can be mutated, then we have to protect the state. If it is immutable, we have to work on the coordination of multiple threads if the state can be mutated. Now the question is, how do we do that? We will cover the how part in the upcoming videos when we cover the concurrent utilities. Here we are simply focusing on the fundamentals and the theory part. Before moving on to the next topic, let's quickly see a demo of what we have covered so far. So in this quick demo, we will see how multiple threads working on the same data can make things complicated and they can make things inconsistent. So here we have a simple class, lost update, and in this class we have another inner class, integer holder. And if you notice this inner class, it has a simple integer variable, some value, then two methods, one to update the value and the second method to get the value. Now what will happen, anyone wanting to update the sum value will call the update value method by passing the new value, which will simply update the sum value, the integer variable of this class. Now if you notice, this integer variable, because this is an instance variable, represents the state of this class. Okay, so the state of the class is determined by this integer variable, state of this class. Now in the main method, we are creating two threads. We are starting two threads, T1 and T2. And here we are creating a new instance, new object of integer holder class. But if you notice, these two threads, T1 and T2, are working on the same holder object. What that means is that multiple threads are now sharing the same object. They are working on the same object. And now they are calling the update value method. So that means not only they are working on the same object, but also they are updating or mutating the state by calling the update value method. Both the threads will try to update the sum value, okay, by passing a new value. So what T1 is doing, it is passing value 1, and what T2 is doing, it is passing value 2. So the expectation of thread T1 is that when I call holder.update value by passing the value 1, the internal value will be updated to 1, and when I call the get some value method, I should get the value 1. And similarly, the expectation of T2 would be that the internal value will be updated to 2. So when I get the value by calling get some value, I should see the value 2. Okay, so here we have the scenario of shared and mutable state, because the same object of this integer holder class is shared and its state is mutable. T1 and T2, both the threads are updating the value by calling the update value method. Now if you notice, for the thread T1, we have introduced an additional delay of 5 seconds. This basically represents the delay or maybe the context switch that could happen between T1 and T2. We will explain, we will see what is the meaning of this delay. But let's say if we run this program, what do you think will happen? Thread T1, when it calls the get some value method, will it see value 1 or value 2? So let's rerun. So here we can see that for T1, the value is 2, and for T2, the value is also 2. The expectation of T2 is fine because T2 was the one who updated the value to 2. But if you think from the T1 perspective, T1 updated the value to 1, but it is getting the value back. So this could fail the operations or the decisions of thread T1. So here, because the internal state is mutable and it is shared across multiple threads, so we see the problem of the lost update. Here the update of thread T1 got lost. Now let's understand why this could happen in a multi-threaded environment. So what is happening here, thread T1 is calling the update method here and thread T2 is calling the update method here, and both are passing different values 1 and 2. Now what this delay represents, suppose, because we know both the threads are independent units of execution, so they will be executed concurrently. Now what could happen, let's say thread T1 got a chance to execute on CPU and this line was executed. So for thread T1, it will pass the value 1 and the internal value of integer holder will be updated to 1. So let's say at time T1, for thread T1, the value is 1. Okay, now what could happen that before T1 gets a chance to execute this line to get the value back, there are multiple possibilities. The first possibility is maybe there was a single core. So there was a context switch, T1 was switched off and T2 gets a chance to run its execution, and maybe T2 was able to run the whole block in one go. So that means while the value was T1, because T2 executed, so at time T2, okay, for thread T2, the value became 2. And now because the value is common, the updated value is 2. Okay. And then after some time, after the context switch, when T1 resumes the execution and executes this line, it will now see the value 2 because it has been changed. Or maybe there was no context switch, But before T1 can execute this piece of code, maybe T1 and T2 both were running on separate cores, separate CPU cores. And there was some delay for some reason. Before T1 could execute this line, T2 on a different core completed the execution and updated the value to 2. So when on a different CPU core, T1 gets a chance to run this line, it will again see the value 2 because this has been updated as we discussed. So there are multiple possibilities why this could happen. But the thing is, when you have the shared and mutable state across multiple threads, we can see the problems of lost update or some kind of inconsistencies. And that's why, due to this custom delay of 5 milliseconds, what we see when T1 executes this line, we see the value 2 for both the threads. For T2, it is fine. But for T1, the expectation is false because it was expecting the value to be 1. Okay, so that is the problem of lost update, shared and mutable state. So far, we have covered the use case and the scenario of shared and mutable data when multiple threads are accessing the same content and updating it. Now, let's see what else can go wrong in a multi-threaded programming environment. So here we have a very simple class, dummy class, which has two variables, flag1 and flag2. The default values are 0. Then it has a method setValues in which we are updating the value of flag1 to be 1 and flag2 to be -1. And then we have the method doSomething, which has some logic using flag1 and flag2. Now let's see what happens when there are multiple threads. Let's say thread T1, which is calling setValues method. That means thread T1 is updating the values of flag1 and flag2. Then there is second thread which is calling doSomething. So one thread is updating the values of flag1 and flag2, and another thread, the second thread, is calling doSomething, which basically the implementation depends on flag1 and flag2. So while the values of flag1 and flag2 are being changed by thread T1, what do you think will happen to the values of flag1 and flag2 in this method? So for example, here the default values are 0, 0. Then let's say thread T1 is changing the values to 1 and -1. And then thread T2 is calling this method. So what do you think will happen to flag1 and flag2? So for example, depending on the order of execution, do you think the value of flag1 and flag2 will be 0, 0? That means before T1 executes this block, will the thread T2 see the actual default values, that means 0, 0? Or do you think T1 will be executed successfully, so the value of flag1 will be 1 and flag2 will be -1? Now that is the assumption that we generally have when we declare the variables and when we write the code, because we think the lines will be executed serially and as a chunk in a block. Suppose what happens when T1 is executing this method, so it could only execute flag1. Okay, but at the same time T2 also executed this particular method doSomething. So that means the value of flag1 will be changed to 1, but flag2 is still 0. This is one possibility. Or what happens if for thread T1 this block is executed first? That means what if this value is set first? In that case, what thread 2 will see, it will see the -1 value for flag2, but flag1 is still 0. So you see there are two more possibilities where flag1 could be 1, but flag2 could still be 0, and where flag2 will be set first, so it will be 0 and -1. Okay, and if everything happens correctly, then in that case we will see 1 and -1, which is the expectation, or 0 and 0. We need to understand that these two possibilities are genuine and it could happen in a multi-threaded environment. Now you might be thinking why this line will be executed first before this one. So this is something called reordering of statements. Okay. Now what is this reordering of statements? Reordering of statements is that these statements will be reordered. They will be executed in any random order. And this is permissible by the compiler, JVM, and even CPU can execute these statements in different order. Now why this could happen? So for example, if we just focus on these two lines, here we are initializing flag1 first and flag2 0. This is what we have written as part of the class. But the thing is, compiler, JVM, and CPU knows that these two statements are independent. They are not related to each other. There is no dependency. So they are free to execute them in parallel in any order. So it could happen that this line will be executed first, so it will be initialized first and flag 1 will be initialized later. This is entirely possible. And similarly, if we focus on the set values method, as I said, flag 1 and flag 2 are independent. So these two lines can be executed in parallel by JVM and by CPU. So it is entirely possible that this line will be executed first, which will set the flag 2 to -1, and this line will be executed after this one. So it is entirely possible that while the value of flag 2 was -1, flag 1 was still 0 at the time when T2 executed this code. So you see, all these things are possible in a concurrent program, and this is something that we need to understand, especially when we are dealing with a multi-threaded program. So this is called the reordering of statement, and this can happen on the compiler level, on the JVM level, even on the CPU level. Now there are ways to prevent this reordering. Suppose we can have some sort of control that this particular block should be executed in the same order, so no reordering should happen. And we will cover these things when we cover the hands-on, when we will cover the concurrent utilities like synchronization, locks, and other synchronizers. So for now, just keep this thing in mind, that this is another thing that can go wrong if not handled correctly and carefully. This is called the reordering of statements. So far we have covered a lot of details about thread safety, and in the next video we will cover the remaining bits like race condition and atomicity and visibility before we start covering the concurrent utilities and hands-on. So that's all for this video. See you in the next video. Thanks for watching.